the lie of the void. Imagine that absolute emptiness, the vacuum of space, is actually bubbling with invisible energy capable of creating matter from nothing. What if the most fundamental concepts of reality that we were taught turned out to be wrong? And the truth is so strange that many scientists avoid discussing it. Today, I invite you to look into a place where we have always thought there was only silent nothingness, and discover a whole world hidden from our eyes, a world that turns everything upside down. We are used to thinking of emptiness as the absence of everything. No air, no light, no matter, just a gaping blackness between the stars, or a perfect vacuum that physicists try to create in laboratories by removing every molecule. This intuitive understanding seems so natural, so unshakable. Emptiness is the backdrop, the stage on which the drama of the universe unfolds, but it itself is inert, passive, dead. Right. But quantum mechanics, the strangest and most counterintuitive field of science, tells us, no, that's incorrect. Completely incorrect. Beneath the veil of this apparent emptiness lies an ocean of seething activity, a fundamental level of reality that determines the properties of everything that exists. This notion begins to dismantle your familiar view of the world. We ask the main question, what truly lurks there, where according to all our everyday notions, there should be absolutely nothing? Prepare yourself, for what we discover is capable of shaking the very foundations of your worldview. This is knowledge that both frightens and fascinates, prompting a reevaluation of the nature of space, time, and matter itself. We embark on a journey to the heart of the vacuum to see its true living face. An ocean beneath the veil of reality. Now let me take you even deeper, to the very foundation of our existence, by introducing the concept of quantum fields. Forget for a moment about the tiny particle balls flying in the void, as we were taught in school. Quantum field theory paints a completely different picture, much stranger and more elegant. According to it, the fundamental reality is not particles, but fields, invisible entities that permeate absolutely all of space-time, like vast, invisible oceans. There are fields for every known fundamental particle. The electron field, quark fields, photon field, electromagnetic radiation field, Higgs field, and so on. They are everywhere, even where we see absolute emptiness. Elementary particles, such as electrons or photons, are nothing more than local excitations or quanta of these fields. Imagine a calm surface of a pond. This is the field in a state of rest, in a vacuum. Throw a stone, and ripples, a wave, will run across the water. This ripple is a localized disturbance, and is analogous to a particle. An electron is a quantum of excitation of the electron field. A photon is a quantum of excitation of the electromagnetic field. Particles can be created and disappear, but fields always remain. They are the true fabric of reality. This concept completely changes our understanding of matter and interaction. The interaction between particles is the exchange of quanta of the corresponding fields. For example, two electrons repel each other by exchanging virtual photons, quanta of the electromagnetic field. This is not just a convenient mathematical model. It is a description of how the world is structured at the most fundamental level, confirmed by countless experiments with astonishing precision, reaching 1/10,000,000,000 of a percent. In some cases, we no longer live in a world of separate objects floating in a void. We live in a world of interpenetrating, vibrating quantum fields, and everything we see and feel is merely a manifestation of their complex dance. The ever-watchful abyss, zero-point energy. Energy, born from absolute zero, that's what we will now examine. If quantum fields are the fundamental fabric of reality, as I described earlier, then what happens to them in a state of absolute emptiness and cold? Intuition suggests they should freeze, calm down, and reach a state of complete zero energy. But the quantum world once again challenges our intuition. Recall one of the strangest and most fundamental principles of quantum mechanics, the Heisenberg uncertainty principle. It states that a quantum system cannot have certain pairs of properties, such as position and momentum, precisely defined at the same time. The more precisely we know one, the less precisely we know the other. This is not a limitation of our measurements. It is a fundamental property of nature itself. So, this principle also applies to quantum fields. A field cannot simultaneously have a precisely zero value and a precisely zero rate of change of that value. It cannot simply freeze at absolute zero. It must constantly oscillate, fluctuate even in a complete vacuum and at the temperature of absolute zero, which is minus 459.67 degrees Fahrenheit, the lowest theoretically possible temperature. These unavoidable quantum fluctuations of fields have a minimal non-zero energy. This is called zero-point energy or vacuum energy. This is not thermal energy that can be removed by cooling. It is an inherent property of spacetime itself, permeated by quantum fields. Imagine a perfectly calm lake. Even on its surface, there will always be a slight ripple caused by the very existence of water. So is the vacuum. It is not dead, it breathes with quantum fluctuations. This zero-point energy fills the entire universe. Its calculated magnitude, according to some theoretical models, is simply colossal, unimaginably huge, but we will discuss this paradox later. For now, it's important to realize the fact itself. The void is not empty. It contains energy. Fundamental, irremovable, inherent to the very structure of reality. This knowledge overturns our understanding of nothingness, transforming it into something active and potentially powerful. The ghostly touch of the vacuum. The whisper of the vacuum, heard for the first time, became a true revelation for physicists. For a long time, zero-point energy remained purely a theoretical concept, a mathematical artifact of quantum field theory. Many believed that it might not have any real physical manifestations, that it could simply be subtracted from the equations as some background level, not affecting observable phenomena. But in 1948, Dutch physicist Hendrik Casimir made a remarkable prediction that hinted for the first time that vacuum energy is not just an abstraction. He considered a very simple, at first glance, system. Two perfectly smooth, parallel, uncharged metal plates placed in an absolute vacuum at an extremely small distance from each other. Imagine a gap thinner than a human hair, divided into hundreds or even thousands of parts. We are talking about distances on the order of micrometers or even nanometers. According to classical electrodynamics, there should be no forces arising between uncharged plates. Gravitational attraction between them is negligibly small. It would seem that they should just hang in the void, not affecting each other in any way. However, Casimir, relying on quantum theory, concluded that a small but measurable attractive force should arise between the plates. A force that literally arises from nothing, from the void between the plates, where it comes from. Casimir suggested that this is the manifestation of the zero-point energy of those very quantum fluctuations, the vacuum. The plates, being close to each other, act as a resonator. They limit the possible long wavelengths of virtual particles that can exist in the gap between them. Outside the plates, there are no such restrictions. This creates a difference in vacuum pressure outside and inside, which pushes the plates towards each other. Just think about it. The void presses. This idea was so revolutionary, so contrary to everyday experience, that it sparked great interest and debate in the scientific community. Casimir's prediction paved the way for experimental verification of the existence of vacuum energy and its ability to perform real work. It was the first step towards understanding that the vacuum is not just a passive arena, but an active participant in physical processes. A sea of ghost particles. So how exactly do these two simple plates in a vacuum manage to attract each other? Let's try to paint a picture of this amazing mechanism using the concept of virtual particles. Remember, I mentioned that quantum fields constantly fluctuate even in a vacuum, possessing zero-point energy. Heisenberg's uncertainty principle, when applied to energy and time, allows for brief violations of the law of conservation of energy. The vacuum can sort of lend energy for a very short period of time, enough to create a particle-antiparticle pair. These particles are called virtual because they exist only for a moment, almost instantly annihilating each other, and returning the debt to the vacuum. They are not real particles that we can observe directly and for a long time, but their fleeting existence has very real consequences. Imagine the vacuum as a boiling ocean of these virtual particles, constantly appearing and disappearing everywhere. Now let's place our two closely positioned plates in this ocean. The space between the plates acts as a resonator or filter for these virtual particles, more precisely for the waves of quantum fields they correspond to. Only those virtual particles or field waves whose wavelength fits an integer number of times between the plates can exist there. Long wavelength fluctuations are suppressed. Outside the plates, there are no such restrictions. There, the full spectrum of virtual particles of all possible lengths, waves, and energies can boil. It turns out that outside the plates, there are seemingly more virtual particles. Their activity is higher than in the narrow gap between them. This excess activity outside creates pressure that literally pushes the plates into each other. This is the Casimir force. a macroscopic manifestation of quantum vacuum fluctuations. A force born from emptiness, confirming that this emptiness is not empty at all, but full of hidden energy and activity capable of moving objects. This is not magic. This is physics at its deepest and strangest level, demonstrating the power hidden in what seems like nothing. Proof: the void is alive. Hendrik Casimir's prediction was elegant and intriguing, but it's one thing to have a theory on paper, and quite another to have real observation. The Casimir force is extremely weak at ordinary distances, becoming noticeable only when objects are separated by a distance on the order of a micron or less, which is thousandths or even millionths of an inch, comparable to the size of bacteria or the thickness of individual layers of graphene. Measuring such a weak force arising between two closely positioned surfaces was an incredibly challenging experimental task. It required the highest precision, elimination of all possible interferences, vibrations, electrostatic charges, and temperature fluctuations. Physicists struggled with this problem for decades. The breakthrough came in 1997 when Steve Lamoureux, who was working at the University of Washington at the time, managed to conduct the first high-precision experiment. He used an ingenious setup with the torsion pendulum, a sensitive device capable of measuring very small forces by the angle of twist of a thin fiber. In his experiment, the force of attraction was measured between a carefully polished spherical lens and a quartz plate, both coated with a layer of metal. By bringing them to micrometer distances, Lamoureux was able to register a tiny force of attraction, which matched Casimir's theoretical prediction with an accuracy of about 5%. This was a triumphant confirmation. Vacuum energy is real, and it truly does create a force. In the following years, other research groups, using even more advanced techniques such as atomic force microscopy, confirmed the Casimir effect with even greater precision and for various surface geometries. Today, the Casimir effect is a firmly established physical fact, routinely taken into account, for example, in the design of micro and nanoelectromechanical systems, where it can lead to undesirable sticking of parts. It is no longer just a shocking theory, but a real phenomenon that has proven that the void possesses energy and exerts pressure on the material world. The vacuum is alive. The birth of matter from nothing. Now we approach an idea that seems straight out of science fiction: the creation of matter from pure emptiness. If the Casimir effect showed us that the vacuum can exert pressure, then the next step in our exploration into the quantum abyss is even more astounding. This is about the Schwinger effect, a theoretical possibility of literally pulling real, full-fledged particles from the bubbling ocean of virtual pairs in the vacuum. This prediction was made by American theoretical physicist Julian Schwinger, one of the titans of quantum electrodynamics, who received the Nobel Prize in 1965. Here's what his idea is about. If you create an extremely, unimaginably strong electric field in a vacuum, it can affect the virtual particle-antiparticle pairs that are constantly being created and annihilated. Imagine a virtual electron-positron pair. Under normal conditions, they are doomed to almost instant mutual destruction, but an ultra-strong field can pull them apart before they have a chance to annihilate. The field transfers enough energy to the pair to turn them from fleeting, virtual phantoms into real stable particles that can be observed and measured. They sort of materialize from the energy of the field and the energy of the vacuum itself. This is not just a change in vacuum pressure, like in the Casimir effect. This is an act of creating matter from the energy permeating the void. The electric field acts as a catalyst, a trigger, releasing the potential hidden in quantum fluctuations. The very idea that you can create something from nothing just by applying a strong enough field excites the imagination and forces a reevaluation of the fundamental laws of conservation. Schwinger showed that the vacuum is not just a passive reservoir of energy, but a potential source of matter itself, merely waiting for the right conditions to manifest. The cost of creating a world. What are these conditions capable of awakening matter from non-existence, as Schwinger predicted? The answer is simple and at the same time frightening. Truly extreme conditions are needed. Fields of such intensity that are rarely found in the universe. There is a critical value of electric field intensity known as the Schwinger limit. Its magnitude is approximately 1.3 times 10 to the 18th power volts per meter. To try to imagine this colossal number, this field is quadrillions of times stronger than the fields we can create in laboratories using the most powerful lasers or particle accelerators. It even far exceeds the fields inside atoms that hold electrons in orbit. Such fields can exist, for example, near exotic astrophysical objects like magnetars, neutron stars with incredibly strong magnetic fields. Why is such monstrous intensity required? The answer lies in Einstein's famous equation, E equals mc superscript 2, linking mass and energy. To create a pair of real particles, for example, an electron and a positron, energy equivalent to their rest mass is required. Rest. This energy must be provided by the electric field over a very small distance, comparable to the Compton wavelength of the particle, a characteristic quantum scale. The Schwinger limit corresponds to the field strength capable of performing such work on a virtual pair, bringing it into reality. This enormous value vividly demonstrates the colossal energy trapped in the vacuum, given that such titanic efforts are required to release it in the form of particles. We see an ocean of zero-point energy, but extracting even a drop of it in the form of real matter turns out to be incredibly difficult. That is why the Schwinger effect has not yet been observed directly in its pure form in the laboratory, although indirect evidence and similar processes are studied by high-energy physicists. The difficulty of reaching the Schwinger limit highlights both the enormous potential of vacuum energy and our current limitations. In its exploration lies the greatest mistake of the universe. And here, at the intersection of quantum theory and cosmology, we encounter a mystery of such depth that it causes many physicists to experience intellectual discomfort, and some outright awe. I am talking about the cosmological constant problem, possibly the greatest failure of the predictive power of modern fundamental science. We have established that the vacuum is filled with zero-point energy, quantum fluctuations of all existing fields. Quantum field theory even allows us to estimate the density of this energy. When physicists try to do this, summing the contributions of zero-point fluctuations of all known fields up to a certain energy limit, they get a number. For example, the Planck energy, which is considered the boundary of the applicability of our theories. The number is so absurdly, monstrously huge that it's hard to even comprehend. By some estimates, the theoretical energy density of the vacuum exceeds the observed energy density in the universe by about 120 orders of magnitude. That's a 1 followed by 120 zeros. To give you an idea of the scale of this catastrophe, this discrepancy is greater than if you were trying to measure the length of a small virus, with the precision of the size of the entire observable universe, and got it wrong. This theoretically predicted vacuum energy should have had a colossal gravitational impact. If it were indeed that enormous, its anti-gravitational effect should have torn the universe apart. Practically at the moment of its birth, since vacuum energy behaves like a medium with negative pressure, space would have expanded at such a furious rate that neither galaxies, nor stars, nor even atoms could have formed. But here we are. The universe exists, it is expanding, but with a much more modest acceleration that corresponds to the observed density of dark energy or the cosmological constant. This observed density is tiny compared to the theoretical prediction. It is smaller by those very 120 orders of magnitude. Where did all this gigantic vacuum energy go? Why is its gravitational effect almost completely compensated? Is there some unknown mechanism or fundamental principle that reduces it to the observed value? Or is our quantum field theory fundamentally wrong when it comes to gravity? This is the deepest crisis, a gaping chasm in our understanding of the very foundations of the universe. And no one has an honest answer yet. To touch the infinite source? An inexhaustible ocean of energy right beneath us, in every cubic inch of space. Is it possible? Since the vacuum is indeed filled with colossal zero-point energy, even though its observable gravitational role is mysterious, a tempting question arises. Can we learn to extract and use it? The very idea seems fantastic, almost mythical, a source of pure, limitless energy that will never run out. Imagine a world where humanity's energy hunger is forever satisfied, where there is no need to burn fossil fuels, polluting the planet, where space travel becomes more accessible thanks to an inexhaustible source of propulsion. This is a dream that has stirred the minds of inventors and science fiction writers for centuries, and quantum physics seems to provide it with some theoretical foundation. After all, energy exists. It is real. The Casimir effect is proof of that. But here we are faced with the harsh reality of physical laws and technological barriers. Firstly, as we have already seen with the Schwinger effect, stirring the vacuum and making it release energy in the form of particles requires truly astronomical efforts. Secondly, the fundamental laws of thermodynamics state that to obtain useful work, an energy difference is usually required, some gradient or transition from a high-energy state to a low-energy state. The vacuum, however, represents the fundamental, lowest energy state of the system. How can we create a state with even lower energy so that the vacuum can release its energy? It's like trying to make water flow uphill without a pump. There are various speculative ideas, such as using a modified Casimir effect to create tiny engines or attempting to locally alter the structure of the vacuum. However, all of them are at the very edge of theoretical physics, often bordering on violations of known conservation laws or requiring exotic conditions and materials that are not available to us. At the moment, there is not a single experimentally confirmed method of extracting useful energy from the vacuum. Although zero-point energy is real, its use remains deeply hypothetical and faces fundamental difficulties that may prove insurmountable. The dream of free energy from the void remains just a dream for now, although it is based on the astonishing discoveries of quantum physics. Warping space with the void. But what if the potential of the quantum vacuum extends far beyond a simple energy source, affecting the very fabric of space-time? Here we enter the realm of the boldest, most exciting, and at the same time, the most speculative hypotheses of modern theoretical physics. Some scientists wonder if manipulating the quantum vacuum could allow us to create exotic forms of matter or energy with incredible properties. One of these hypothetical properties is negative energy density, or negative mass. According to Einstein's general theory of relativity, such exotic substances are necessary to create and stabilize fantastic objects like traversable wormholes, theoretical tunnels through spacetime that allow instant travel between two distant points. In the universe, they are a kind of cosmic shortcut. Negative energy is also the basis of the warp drive concept proposed by Mexican physicist Miguel Alcubierre in 1994. His idea involves creating a bubble of spacetime around a spacecraft that would compress space in front of the ship and expand it behind. The ship itself inside the bubble would remain stationary relative to the local space, but the bubble itself could move at speeds exceeding the speed of light without violating Einstein's postulates locally. It sounds like science fiction, and in many ways it is. Creating negative energy is a colossal challenge. We have never observed it on macroscopic scales. However, some theoretical studies suggest that certain configurations of the quantum vacuum, such as those arising in specific geometries of the Casimir effect or in so-called squeezed vacuum states, can locally possess negative energy density. These effects are extremely small and unstable, but they provide food for thought. Is it possible that one day we will learn to manipulate the vacuum to such an extent that we can create and maintain such exotic states on macroscopic scales? This would pave the way for technologies that today seem like magic to us, such as superluminal travel and instantaneous communication. Perhaps even time travel. For now, these are just distant horizons of theoretical thought, but they show what incredible prospects understanding and controlling the most fundamental energy of the universe might hold. The void. Reality, in fragments. The quantum vacuum compels us to ask the deepest questions about existence, shattering the familiar foundations of our worldview. All these discoveries related to zero-point energy, the Casimir and Schwinger effects, and hypotheses about extracting energy or manipulating spacetime have not only scientific but also profound philosophical significance. They fundamentally change our understanding of reality itself. Think about it. The concept of absolute emptiness, nothingness, which has been the foundation of many philosophical and scientific systems. For millennia, it turns out to be untenable. What we considered a passive background, an inert stage for action, is actually a dynamic, active environment, a fundamental ocean of energy from which matter itself is born. The boundary between something and nothing becomes blurred. Emptiness becomes not the absence of being, but its potential form, the source of all that exists. This turns our intuitive notions of creation and existence upside down. If particles are merely ripples on the surface of ever-fluctuating quantum fields permeating the vacuum, then what is primary, matter, or the field? Substance or structure? The very concept of a thing becomes more blurred, giving way to the concept of process, interaction, excitation. Our classical intuition, shaped by the experience of interacting with macroscopic objects, turns out to be completely inadequate for describing fundamental reality. The world at the quantum level does not adhere to conventional logic. Either or. It is full of paradoxes, uncertainty, and the interconnectedness of everything with everything. The quantum vacuum is perhaps the most striking manifestation of this strangeness. It shows us that reality is much more complex, deeper, and more astonishing than we could have imagined. This knowledge is both awe-inspiring and evokes a sense of wonder, perhaps even a slight dizziness from realizing how far our everyday perceptions are from the true nature of the world. We are forced to acknowledge the limitations of our intuitive understanding and embrace the universe in all its counterintuitive beauty, where even emptiness is full of life and infinite potential. The reality as we knew it is indeed crumbling before our eyes, giving way to a new, deeper, and more mysterious picture of the world. The burden of knowledge, science on the edge. So why did I choose such a provocative title? Scientists are afraid to discuss it. Is there really a conspiracy of silence or fear of the truth? Hidden in the depths of the quantum vacuum. Let me explain. The word afraid here, of course, should not be understood literally as emotional fear. It's about something else, about profound scientific caution, intellectual honesty, and the enormous responsibility that falls on the shoulders of researchers working at the very forefront of knowledge. When we talk about zero-point energy, the Casimir effect, or even the theoretical possibility of the Schwinger effect, we are still on more or less solid ground, confirmed by experiments or rigorous calculations within established theories. But as soon as the conversation turns to the practical extraction of energy from the vacuum, the creation of negative mass, wormholes, or warp drives, we inevitably enter the realm of high speculation. These are exciting, imagination-stirring ideas, but they are often based on extrapolations of existing theories far beyond their proven applicability or require conditions that we have no idea how to create. Scientists exercise restraint because science demands evidence, not just beautiful hypotheses. Another reason for caution is the colossal difficulties or even the fundamental impossibility of experimentally verifying many of these ideas in the foreseeable future. How can we test the existence of a traversable wormhole or measure negative energy density on macroscopic scales? Without the possibility of experimental verification, a hypothesis risks remaining merely a mathematical exercise, no matter how elegant it may be. Furthermore, we must not forget about fundamental unresolved problems, such as the monstrous discrepancy in the cosmological constant problem. This conflict between the predictions of quantum field theory and the observations of general relativity shows that our understanding of the interaction between vacuum and gravity is fundamentally incomplete. Making bold statements about the properties of the vacuum while ignoring this gaping chasm in our knowledge would simply be irresponsible. Finally, there is also a very pragmatic reason for restraint, protecting the reputation of science from pseudoscientific speculations and unfounded hype. Topics like energy from the vacuum or anti-gravity are easily picked up by people far removed from science, generating a wave of misinformation, fraudulent schemes, and false hopes. Serious scientists prefer a measured and precise formulation to avoid giving charlatans reasons for such distortions. Thus, the fear of scientists is not a fear of truth, but a fear of error, a fear of mistaking wishful thinking for reality, a fear of undermining trust in the scientific method. It is the caution of a pioneer who understands that they are in uncharted territory, where every step requires careful verification and consideration.